Hi there, I'm Micaela Kaplan, the ML Evangelist at HumanSignal, and this is In the Loop, the series where we help you stay in the loop with all things data science and AI. This week, we're going to look at Markov models, which form the base of a lot of concepts in traditional machine learning, including reinforcement learning, which we covered last time. Let's get started. Markov models are named for Andrei Markov, the Russian mathematician who researched them. There are 4 common types of Markov models which are used in different situations, depending on whether every state is observable or not, and whether the system is adjusted on the basis of the observations made. Today, we're only going to look at cases where the system state is fully observable, Markov chains and Markov decision processes. We'll dive into hidden Markov models next time. In order to understand Markov models, we need to understand the Markov assumption. Essentially, the Markov assumption says that when predicting the sequence of events represented by the model, only the previous state matters. More formally, the probability of the state Qi being equal to A, given a set of n states, is the same as the probability of the state Qi being equal to A, given just the previous state. This is like saying that to predict a sentence, the only word that matters is the word that you just said, not any of the other words. Now that we know the Markov assumption, we can dive into Markov models. We'll start with Markov chains, the simplest of the Markov models. Essentially, a Markov chain is a model that tells us about the probabilities of sequences of random variables. We call these random variables states. Each state can have a value from some set. In NLP use cases, these might be groups of words, but it could also be anything. The weather, whether a day will be hot or cold, is another frequent example of Markov chains. According to the Jurafsky and Martin Speech and Language Processing textbook, Appendix A, a Markov chain is formally defined as follows. Big Q representing a set of n states, where each state is represented by little q sub I. Big A representing the transition matrix, where each little a sub ij represents the probability of moving from state I to state j, such that for each state I, the sum over all states j of the transition probabilities from state I to state j is equal to 1, and pi, an initial probability distribution over the states, where pi sub I is the probability that the system starts in state I. Some states may have 0 for this value because it may not be possible to start in that state. Additionally, the sum of the pi values must be equal to 1. This is helpful, but Markov chains are easier to understand with an example. Let's imagine we're looking at the weather. For our big Q set of states, we have 3, hot, cold, and warm. For our transition probability matrix, big A, there are a total of 9 transitions as shown on the screen. These are often identified experimentally or provided in an example. Here, we had ChatGPT generate a random example for us. Finally, we need pi, the initial states. This is the probability that we start the chain in some state. Here, ChatGPT generated the following random set. Pi is equal to 0.3 for hot, 0.4 for cold, or 0.3 for warm. Markov chains are called chains because the states can be chained together via their transition probabilities. The image on the screen shows what the visualization of this example Markov chain would look like. Now, let's do a quick math example. Let's say we want to find the probability that the weather for 4 days is hot, warm, hot, and then cold. First, we get the probability that we start with a hot day, 0.3. Then, we need to multiply it by each of the relevant transition probabilities. First, the probability that we go from a hot day to a warm day is 0.2. Then, the probability that we go from a warm day to a hot day is 0.3. Finally, the probability that we go from a hot day to a cold day is 0.2. This gives us the following equation. The probability of hot, warm, hot, cold equals 0.3 times 0.2 times 0.3 times 0.2 equals 0.0036. Now that we've covered Markov chains, let's look at Markov decision processes. Markov decision processes are used to describe how decision-making agents, like robots or game-playing machines, move through a system while trying to achieve a goal, but where the outcome of the decision is uncertain. In environments where Markov decision processes are useful, an action might lead to a different result each time. Like a Markov chain, a Markov decision process relies on the Markov assumption that the next action only depends on the previous action. It starts with a series of states, telling you what position the system is in. They also have a transition model, which is similar to the transition probabilities matrix of a Markov chain. In the transition model, we use probabilities to model what might happen as the outcome of some decision. There are a few other key components of a Markov decision process. The action set, which in this case we use big A for, tells us all the different actions that the agent of a system can take at any given time. There's also the reward function, big R, which models if the action that the agent took was good or bad. This is defined by the writer of a system on a case-by-case basis, depending on what they want to optimize the agent to do. For example, an agent might get +1 points for reaching a goal or -1 points for stepping into a danger zone. Finally, Markov decision processes have a policy, which we use pi for. The agent learns this policy, looking for one that optimizes the total reward over time. We use the Bellman equation to figure out the optimizations for each state at each time. When we run the algorithm, we do a value update and a policy update, repeating each step until the policy eventually converges. And that's it! Markov chains and Markov decision processes are both helpful ways of working through problems where we can observe the outcome of an action. Join us next time, where we'll talk about hidden Markov models, which work when the system is only partially observable. That's all for this week. Thanks for staying in the loop. Want even more in the loop? Check out our other videos. Don't forget to like and subscribe to stay in the loop.